1, 2. One, two. Yeah.
All right. I didn't manage to make a separate assignment announcement slide for today, but basically, I mean, the usual announcements are, so there's the deadline coming up. So for P3, it's on Sunday, I think, the deadline, and yeah. Start talking to each other about forming teams for the for the next assignment. Are there any questions before we start a new chapter today? Well, on first order logic, do you have any questions about assignments, about the course in general? Okay, no, nothing. So today we'll talk about first order logic, which is something I would say much more fun and interesting than a propositional logic, and it's much more powerful. It's a much more powerful framework. We'll see very shortly how it all works. So the main limitation about the previous logic we're talking about so far is that it's a weak language generally. It's not expressive enough. We cannot express all kinds of concepts. For example, we cannot say that some things like, you know, for all X they have a property, you know, like all animals are on Earth, for example, or like, you know, yeah, or all cats are animals, for example. These are things we cannot say with propositional logic, but we can say with first order logic. So in general, in the propositional logic, what we saw before is how to identify individuals like Mary or 3. We cannot talk directly about properties of individuals or relations between individuals like the list all. Generalizations, patterns, regularities, and so on cannot be easily represented. For example, all triangles have 3 sides. Oh, I mean, this is true. We cannot easily express that with the previous logic we were talking about so far. So first order logic, which is abbreviated as FOL, is expressive enough to concisely represent this kind of information. So we can add the relations we can have the relations, variables, and quantifiers in particular. So we can say things like every elephant is gray, which is expressed in first order logic as for all X, elephant of X implies gray of X. This is how we express something like, you know, every elephant is gray. What about this one? There is a white alligator. We use a different quantifier here called exists, which means there exists an X, which is alligator of X and white of X. There exists an X, which is both alligator and white, yes.
So could we use and instead of implies in the first one?
In the second, can we use here implies? Is that what you know? Can we use and here instead of implies? That would say something different in English. That would say that all our objects are both elephants and gray. That's what this means. Objects from our domain. We have to be talking always about a domain. XR, for example, like all the animals on the planet or all the entities on the planet, or, you know, we have to speak about domain. And then that would mean that every element in our domain is an elephant and is gray. That's what that would mean. So it would say a different thing in English, but we can't have that as a sentence, and it would be syntactically correct. It would be a correct sentence otherwise. Yeah, any other questions? No? Okay. So let's see. So a bit more. So first order logic models the world in terms of several things, in terms of objects, which are, you know, kind of entities with individual identities, with the properties of objects that distinguish them from other objects. One object is tall, the other one is short, or one is gray, the other one is black. Relations that hold among sets of objects. One object is bigger than another object. Functions, which are a subset of relations where there is only one value for any given input. So in particular, so we only have, each function has to map something to only one single value. And that's how we'll define at least a function here. So objects are, for example, students, lectures, companies, cars. Relations are brother of, bigger than, and so on. Has color, occurs after, owns, visits, and so on. Properties could be blue, oval, even, like even and odd numbers, large, small, and so on. Functions could be father of, best friend, second half, one more than, and so on and so on. These are examples of things we can do with first order logic. How many of you have seen first order logic before, to get an idea? Some people, but not everybody. Okay, that's good. So I'm hoping also that if for some of the other ones, I'm assuming some familiarity with these things, with first order logic before. For those of you who have not seen, maybe try to speak to your colleagues, maybe try to get some help even after the course, you know, try to help each other so you can get everyone up to speed with these. We don't have time in this class to go through like really like fundamentals of first order logic, but yes. Okay. So we also have to be speaking about a domain of discourse. What is the domain of the variables that we're talking about? So so we have, for example, constant symbols which represent individuals in the world. So again, we have Mary, we have three, we have green, we have these all kinds of objects that we're talking about. We have function symbols which map individuals to individuals. So father of Mary is John, for example, or color of sky is blue. So this is a function symbol that maps an individual to another individual. Here we're using this word individuals, but we can sort of think of them as entities more, you know, generally any of these objects that we were talking about. And we also have predicate symbols which map individuals to truth values. So greater of 5,3. So is it 5 greater than 3, true or false? So it is true. So yeah, is green of grass? Yeah, the grass is green. Yes, color of grass green would return true. Otherwise, if it's not green, it will return false. Yeah. So let's just see what is the first order logic syntax. So we have three key things. We have variable symbols, so X, Y, foo, and so on. Then we have connectives, which are the same as in propositional logic, the exact same ones. So we have the negation, we have and, we have or, we have implies, and we have if and only if, the exact same ones. But now we also have something new. We have these quantifiers, which we have the universal quantifier, which is for all X. For all X of something. So for all X, there's something holds for all the objects in our domain. Sometimes you see it written as AX. This is the notation that is less commonly used, but you might see that in some older literature or in older books. We just don't. We will not use this notation. We use this one in this course. And also we have the existential quantifier, which is exist of X. There is at least one object X for which the sentence holds. This is what this means. Again, you also see it written as E of X like that. Okay. So more in more detail. So the universal quantification means that for all X, P of X means that P of X has to hold for all values of X in the domain associated with that variable. So for all X, dolphin of X implies mammal of X, for example. So that means for all values of X, this sentence that comes up has to be true for all entities X in our domain D. here in this case, the domain could be all the different dolphins, in a particular zoo, for example, or in a particular lake, and so on, or not lake, but well, that kind of stuff. And maybe the idea. So existential quantification, the same thing. It says that there exists an x such as p of x, means that p holds for some value of x. There's at least one value of x for which p is true. In the domain associated with that variable. Again, so for example, there exists an x which has mammal of x and lays eggs of x. So there's just an x such that the x is a mammal and lays eggs. And I think it's a platypus, if I'm not mistaken. So platypus is such an animal that is both a mammal and also lays eggs. And in general, it allows us to make a statement about some object without naming it exactly. So we might not know what that is, but we can say something about it. We can say that, oh, there exists something that is both a mammal and lays eggs as well, even if we don't know what it is. This is a bit more of a kind of a slide, more kind of like clarifying some rules and notations. But the idea is sort of like, so I'll let you also maybe go through in more detail at home when, but enjoy. The idea is that we have several rules we have to follow, for example. Well, it's actually more like definition. So a term, we define it to be a constant symbol or variable symbol on an n-place function of terms. So x and f of x1, for example, xn are terms, where each xi is a term. So any of these can be terms. A term with no variables is called a ground term. Okay, some definitions. An atomic sentence is either an n-place predicate of n terms or term equals term. This is what's called an atomic sentence. And a sentence can be either an atomic sentence, one of these, which uses our symbols from propositional logic, and also those that are given by the universal quantifiers, existential quantifiers. And in particular, this last bullet point, any propositional formula has to cannot contain any free variables. So a well-formed formula cannot contain these free variables. For example, they all have to be bound by either a quantifier, an existential quantifier, or the universal quantifier. So, for example, this particular sentence here, for all x r of x y, so here x is bound to the universal quantifier, but y isn't bound. So y is not bound to the universal quantifier, y is free. Yeah, so let me let's do a quick something. Let's do something a bit more complicated just to illustrate that. So let's see if I come up with a formula. Let's see for all x. Yeah, let's do that. R of x Bill let's do that, and yeah, let's say, and then another S of x and Jane. So is this the sentence well formed? No, why? Jane and Bill are free. So yes. Let me add some more clarity. So that's not exactly what I had in mind. Jane and Bill are constants. they are basically or constant. They are a variable. They're basically variables that are exactly that, like atomic, and basically they're just constant, like it already instantiated. They're not like a variable. It's basically instantiated concepts. So here, just x is a variable. Yeah. 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 Exactly. So this means that this universal quantifier here only captures this part. You see, because of the brackets, the universal quantifier stops at the bracket, stops operating after this bracket ends, basically. So then that means that this x here is not bound by the universal quantifier. So this is not well formed. If we had this would have been well formed. If I move this bracket here, then this would have been well formed, because then it would have been bound all the way here. Does it make sense? Yeah. What this is a variable, or yeah, it's somehow that's basically easily solved. Like in general, you have some definition. You have a domain, for example. You have like a set of variables. Like, for example, you define them beforehand to be x, y, z. These are variables, and you know, for example, domain of these variables x, y, z is, for example, Bill, Jane, I don't know, yeah, John, and so on. Like, you know, all the names. So basically, you define these beforehand. These have to be clear and defined. These are the variables. These are the domains of these variables, of all of these variables. They could have different domains. For example, maybe just x and y could be like this. Maybe z, the domain of z is something else. It's a natural numbers, like, you know, 1, 2, 3, and so on. For example, you could have that as well. So you have to define clear domains for each variable beforehand. Yeah. Any other questions? Okay, but that was the main point, is this stops the so yeah, each variable has to be bound by a quantifier like that. If it's not bound by a quantifier, it's not a well-formed formula. Well, it means y is free in this case. Yeah. So in general, universal quantifiers are often, not always, but often used with implies to form rules. So for example, for all x, student of x implies smart of x, which means that all students are smart. So that's how we would translate that English sentence into logic, and vice versa. Universal quantification in general is rarely used to make blanket statements about the world. So for example, for all x, student of x and smart of x means everyone in the world is a student and is smart. Because everyone in our domain in the world would be a student and also smart. It's less often used to make these kinds of statements. Existential quantifiers, on the other hand, are usually used with and to specify a list of properties about an individual. For example, there exists someone who's both a student and smart, which more clear, there is a student that is also smart. And a common mistake is to represent this English sentence as the first order sentence. For example, that there exists of x, there exists an x such as the student of x implies smart of x. What do you think could be the problem with that? If we, what could this mean in English? This sentence, this logical sentence. Yeah. 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 Somebody else? If a student is smart, somebody else, yeah.
Smart can be true.
Yeah, it sounds kind of, this is getting close to, yeah. So in general, if the problem is, because remember, if this is false, then we can have anything, right? False implies anything in general. So what often happens is that this will be true if there's no, if our domain is empty, for example. If we have nobody in the domain, for example, no student in the domain, then this sentence evaluates it true, because there's no, yeah. Or let's say we have X's, but none of them are students. We have all our persons are adults that are not students. So again, the same thing. And in that case, this will always be false, and this will, and then that means the sentence will be true, even though we don't have any students. Does it make sense? Yeah. So, yeah, 1 second. Yes. So quantifier scope. Something very important is that the scope of the quantifiers is generally is very important. So things like switching the order of the universal quantifiers does sometimes change the meaning, not always. So for example, if we switch the order of 2 for alls, if we flip them around, it does the equivalent. It's still equivalent. So they can commute the for alls. We can also commute the exist operators. If we switch the order, we're still good. But if we switch the order of a universal with an existential, that changes our meaning. So for example, if we say for all x, there exists an y such that x likes y. So that means that everyone likes someone. For all x, there exists an y such that likes of xy. So this means exactly that everyone likes someone. But if we flip them around, we get that there exists a y such that for all x likes of xy, this actually means that there exists a y such that all the x's like that person. So that means that somebody is liked by everyone. So it changes the meaning in English if we just flip the two signs. So in general, the universal and existential quantifiers are not commutative. Something very important, they are not commutative. You cannot flip around in their order. It will change the meaning of the sentence. You can do these two, but not this one. Yeah. And there's a few more things we can do with these quantifiers, and in particular, we can apply De Morgan's laws. We have the De Morgan's laws, just as we had earlier with the propositional logic. Now we have them also for first order logic. So if we have an exist that is negated, we can basically put the negation inside and flip it to a for all. Again, the same thing as we happened before. The quantifier changes sign. Same for all. If we negate a for all, then that basically equivalent to an exist of a negated of x. So that means that not for all x p of x. It basically means that there exists an x such that p of x doesn't hold. For all x p of x, again, we can also add a negation at the beginning and flip the operator to exist, and then we also have to negate the p to get the same exact meaning. And same for exist of x p of x. We have to negate at the beginning the whole sentence. We flip the operator for all, and then we negate p of x. And these are all equivalent. So just as we had before with propositional logic, we had these types of inference rules like forward chaining, backward chaining, resolution refutation. We have the same things, the same machinery. We have them also in first order logic. We can use the same techniques. And this is what we're going to do for the rest of the class. So I'll show you unification. We'll do some proofs, and then we'll talk a bit about closure forms, like how it's basically like that's the same as the normal forms that we had before with the with propositional logic. How do we put them into standardized forms? And finally, we'll talk about resolution as such. So how, in particular, resolution refutation. The same idea as we saw before with how we do resolution refutation. We'll do it also for logic. So there's something called universal elimination. One easy thing we can do, which is basically that if we have something like for all x, p of x, then basically we can say that p of c is true for any c that is in the domain of x. So we can always say if we have this, then we can deduce p of c for any c in the domain. For example, so for all x, eats of Ziggy x, we can infer from here that eats Ziggy, ice cream. Or eats Ziggy, pasta, as long as we have those in our domain. So we can replace the quantifier x with any instantiation when we have these universal operators. Okay. Okay. Next one. So existential elimination. What about when we have an exist operator? So from the idea here is that if we have something like exists x, p of x, we can infer p of c because there exists at least some variable c such that this holds. So for example, for all x eats of Ziggy, x, we can infer something like eats Ziggy, stuff. Something we introduce this concept is variable called stuff that basically represents that particular element that existed here, basically. And note that this variable x, now that our variable x has been replaced by a brand new constant. So this is a constant now, which is in particular, which is not occurring in any of the other sentences. So this must not occur in the other sentences in our knowledge base, because if stuff already existed before somewhere else, then it will become linked basically to this new constant we introduced, and we don't want that. We want to introduce a new constant that does not exist from before. This is also called as a columnization. Basically, it's called a column constant, a constant that has not been used previously in the knowledge base. And later on, we can sort of, actually, no, I won't say that because I was going to say we can prove that this column constant is equal to something that does exist in the knowledge base, but that would require some additional inference rules to be applied. And later on, we can prove that stuff was actually ice cream, for example, that we saw earlier, basically. But for now, we don't know what stuff is. It's some kind of constant. Yeah. So the idea is, how do we do now? The question is, how do we automate this process? How do we do automatic inference in first order logic? So just as, kind of programmatically, the way we've seen it being done before. So in particular, the problems are now we have much more complexity in this new setting. Now we have the variables can potentially take an infinite number of possibilities from the domains, like the natural numbers here. Z can be any natural number, for example, an infinite number of them. So there's an infinite number of ways in which we can apply these kinds of rules, so on eliminations and so on. And in particular, there's a theorem called Gödel's completeness theorem, which says that if a sentence is logically valid, then there's a finite deduction or proof of that sentence. So it means that if it is valid, then there's a finite number of steps we can take to prove it. And in particular, resolution refutation is such a procedure we've seen before. Yeah. Any questions so far? Does it make sense? Okay. So let's talk about unification. So how do we do unification, and how can we use it? So unification is basically a pattern matching. You can think of it as a pattern matching procedure. For example, we take two atomic sentences as input and we return failure if they do not match, or substitution list theta if they do match. Let me show you an example. Let me skip straight with the example because it'll make more sense. So let's say we have this sentence: parents of X, father of X, and mother of Bill. And then another sentence: parents of Bill, father of Bill, and Y, right? The idea is that we want to align the two sentences. We want to make them basically, to find the most general common sentence that basically encompasses both of them. So for example, if we instantiate X to be Bill and Y to mother of Bill, we basically get that these two sentences will become equal, basically. So this is the key idea of unification: is what kind of substitutions, or no, assignment, we call it substitutions, can we make to the variables such that we can unify the two sentences? We can make them exactly the same. Yeah. So let's see another example. So let's do another example. So what if we have parents of X, father of X, and mother of Bill, and parents of Bill, father of Y and Z? Can somebody tell me what's the substitutions we need to make to unify them? Yeah. X is Bill. Yeah. Y is X. Yes. And Z is the mother of Bill. Yes. Yeah. X is Bill, Y is also Bill, and Z is mother of Bill. Yes. Yes, it was so you could have done it because you said X is Bill and Y is X. You can also say that X is Bill and Y is also Bill right away, because Y has to be equal to X. So basically, you give it right away the value. But yes. And Z is mother of Bill. Yeah, so X is Bill, Y is Bill, Z is mother of Bill. And now they're unified. What about this one? Parents of X, father of X, and mother of Jane. And with parents of Bill, father of Y, and mother of Y. What about this one? Somebody else? Yeah? Sorry? No valid unification. Yes, why? So X has to be Bill, Y has to be Jane, but X has to be Y, equal to Y. And it cannot be, Bill cannot be equal to Jane. So we do not get a valid unification. So the unification failed in that case. So that's the idea. What about, let me think. What if we do parent of X, Y, let me think, parents with parents of Z and Bill. Yeah, let's do that. So So our substitution will be, so what if, so, okay, so we make y to be Bill, right? Y equals Bill. X equal to Z, right? What if we do this also? What if we do, let's say, theta star? Let's do theta prime. So y equals Bill, x equals Jane, z equals Jane. Is this a valid unifier? So what's the difference? What happened here? What do you mean by certain constant? So actually say that again. A specific value, yes, exactly. So this means that they're both unifiers, but this one is more general than this one. This unifier is more general. So in general, and what in general, what we're interested in is to find the most general unifier, which is called MGU. This is what in general what we want to achieve. The most general one. We don't necessarily want this one, which is too specific, for example. And this is what we mean by the most general unifier and by generality. So, and we'll see. Yeah. Okay. And this is a procedure. This is called the unification algorithm, which basically gives us what's called the most general unifier. That particular. So, and let's see how it works. It's actually do not. Let's look at the example here. So how do we do it? How do we proceed in general? So we go from left to right. So we start from the left hand side, and we try to unify these ones first. So then we make them equal. Once we make them equal, we move on to the next thing. Y equals to Bill, so we have to make them equal. And if these had more elements, again, we move to the next thing, and then we try to make them equal, and so on, up until basically we cover the full expression, the full sentence. So we go from the left all the way, starting from the left hand side, we go all the way one by one and make them equal. So that's exactly the idea with the unification algorithm. So we have two sentences, P and Q. So this is P. So this here would be P, for example. This would be Q. This P sentence 1, Q sentence 2. Let's say it has more than 2 terms, so it has some father of Jane, and so on, and father of W, and so on. So there's some more, and the idea is that we scan for P and Q from left to right, and wherever they disagree. So first of all, and find the first corresponding terms where P and Q disagree. And if there's no disagreement, if we scanned all the way and if we find no disagreement, then we basically return success and return theta with success. If disagreement occurs, if we have a disagreement at terms R and S, then we basically if R is a variable, for example, then we do a union, basically union operator. We basically unify them. We make R to be equal to S. We do the substitution R to be equal to S, and add it to theta, to our substitution list. And then we recursively call this procedure on the remaining, unify it on the remaining sentences. And now with our new unification set theta. And if S is a variable, the same thing. If if none of them are variables, but they still don't agree, we return failure. Why do we return failure? Can somebody tell me why? Why would that be the case? When could it be that R and S are not agreeing, but they're not variables either? Someone? Yeah. What? Give me an example. When would that be? But they're not variables, for example. There's something else. Yeah. Let me say. So what if you have instead of father, what if you have mother? So you have a different function. You cannot unify because the functions are different. This is a father of Jane, this is a mother of W. So you could potentially unify to make W be equal to Jane, but you cannot change the function. You cannot basically change that function to mother to be father. So that's when, but these aren't variables either. And since they're not equal, it's gonna basically return failure there because of something like this. So that's when it would reach when none of them would be variables. Okay. In general, what's very nice about the unification algorithm is that it runs a linear time. So it actually, there's something super nice. And it does find the most general unifier, MGU, and which is the shortest length substitution that makes a two literals match. And also the shortest length, which means the smallest number of substitutions we make, but also the most general ones in terms of how bound they are, like this, for example. Yes. So we don't, we don't give constraint variables, we keep them more general. So in general, there's not a unique minimum length substitution that exists, but at least we know that the unification procedure will find at least one of them that is the minimal length. At least one of them will be found, one of the minimal length ones, not necessarily, there could be other ones. And in particular, something we cannot do, a variable can never be replaced by a term containing that variable. We can never replace x with f of x. So that is illegal. We cannot do that. And this kind of check has to be included in the pseudocode on the previous slide in general. But and before we make this recursive call, so we cannot do this. Okay. Sorry? You cannot do that. No. You still have to keep the f. You can make fx be equal to fy, which basically means that x equals y. So you can make that be the case. It has. I don't understand. Sorry.
So maybe so there's a function there that includes x, and their output is just with x. So basically that's
Oh yeah, you cannot. Yeah, no. Even in this case, you still have to keep f. Yeah. Even in this case, yeah. Even if it's a constant function, it always returns a particular number. Yeah. But in particular, there's something more that we can do with first-order logic, which is we can also apply the full resolution rule that we saw earlier. We saw in the previous class. Remember the full resolution rule when we had multiple statements like P1, P2, Pn, Q1, Q2, Qn. Two of them were complement literals. We could cut them off basically. We could erase them. we can apply the same kind of rule also for first order logic. So this was the first full resolution rule for resolution logic, so P1 or P2 or Pn. And then the other one is not P1 or Q2 or Qm. We basically remove the complement literals, P1 with not P1, and take the rest and OR them all out. So then we get P2 or Pn or Q2 all the way up to Qm. This was previously the rule, the full resolution rule for relational logic. We can apply the same rule also here with first order logic, and it's yeah. So this one sounded complete. The same rule is also sound and refutation complete in first order logic. So given the sentences, again, P1 after Pn and Q1 all the way up to Qm. And if Pj and not Qk can be unified with a substitution list theta, we can unify them and make them complementary literals. Then we get basically this. We can derive all the other ones, P1 excluded Pj here, and here without Qk, with a particular substitution theta that made these equal. So we need to have a substitution theta that makes these complementary literals. For example, so what if we have this clause? So P of x comma f of a, or P of x comma f of y, or Q of y. And we have this other clause, not P of z comma f of a, or not Q of z. Yeah. How do we apply the full resolution rule here? So for example, we can apply it on these two complementary literals, on the first one from the first clause and the first element from the second clause. So these two, this and that. And to do that, what do we have to do for that? So we have to we have to make x be equal to z. That's the first thing. So to unify them. So we use a substitution. We can make x equals to z in the substitution theta, and then we apply the rule. So this gives us. Let's write it on the board. So if we do that substitution, then we get basically what? We get the following. We get P of x comma f of a. So I'm writing the first sentence, or P of what's next? X f of y, or Q of y, or what? And or the other ones in the second clause now, right? Not P of z, but we substitute z for x, right? We can write right away x here. F of a, or not Q of z. Sorry, z was x, no, so not Q of x. Yeah. So, and now because of that rule, so basically, this was a mistake here, sorry. This is an A, right? Yeah, is that true? Yeah. So this one, this term, and these terms are complementary literals. They just negated. This is the negational. This is that negated. So we can basically remove them, and we're left with Q of X, F of Y, or Q of Y, or not Q of X, which is the same as in the black, on the slide, just with Z instead of X. Okay, so that's how we apply it. That's how we apply the full resolution rule in first order logic. Can we let Y equals to Z? Yeah, we can apply it on a Q here. Yeah, exactly. We can also do it there. Yeah. Does everyone see how we can apply it also on the Qs here? Yeah. Okay. Good. So let's move on. How much time do we have? Oh, we have time. Okay, at least half an hour. So in particular here, what I mean by refutation complete means that if the sentences are unsatisfiable, the refutation resolution algorithm will derive a failure, basically. So it's only complete for the unsatisfiable cases. Basically, it will be able to prove those are unsatisfiable only, but only in those cases. If the sentence is satisfiable, it's not necessarily going to derive the correct result. I'm thinking actually, why don't we take a 5-minute break? Because and then we can continue. Because otherwise we have a few more things to go. But we also have a quiz that I prepared for today. So class exercise. So we'll make it a bit more interesting. So in the second half. But let's take a short 5-minute break now. Okay, shall we continue? We do, yeah. We have a few things to just cover now, and then we'll do a exercise at the end. So there's two final things that we still need to cover. So one thing is, so again, we need to understand how do we convert the sentence, the first order logical sentence, to a normal form, like a standardized form for the expression. And in particular, something like this with or. So we want it to look like, P1 or P2 or so, or Pn. And if it has ands, then we simply break it into multiple clauses, if that makes sense. So for example, if we have something like P1 or P2 and P3 or P4, like this, we can simply break it into one clause, P1 or P2, and another clause, P3 or P4. Does that make sense? So we converted one of these longer expressions to two smaller ones. It's basically as if we have a knowledge base with multiple clauses over the and. So that's why we have to get it into ors like that, and with the and we can simply break it into multiple clauses. How do we do that? So there's several ways. For example, we basically do exactly like we did in the first proposition logic. We convert all the if and only ifs to this. So P if only if Q gives P implies Q and Q implies P. We eliminate all the implies connectives. So P implies Q is not P or Q. We reduce the negations. Basically, we simplify the negations. So not P, it is just P. We apply De Morgan's rules, for example, to say not P or Q is not P and not Q, and so on. So we apply all these kinds of rules. These are De Morgan's rules. These are the negated of the negations of the universal and existential quantifiers, which flip the quantifiers in this case. So we get not exist gives us an not for all x gives us an exist of not P, and so on. There's something we also do about the constants. I won't go into this slide. I'll let you read it at home. But the idea is we simply introduce column constants in the existential quantifier. So instead of an exists x p of x, we simply put it as a p of c, where c is a constant that has not been used before. I won't go to this slide again. I'll let you read it at home. But and then we do some more things. For example, we do distributions over or and ands and so on, and we remove some existential quantifiers by moving. We can slide them all to the leftmost. Let's see an example how that will work. So for an expression, so for example, let's say this expression. So we have a super long and complicated first order logic expression. How do we bring it to a normal form, a causal form, a closure form? So the first thing is we eliminate these implies. That's the first step. So this is what changed. So this implies becomes not P of X or the rest. This one also got changed to not P of Y or this. And this implies also got changed to not Q of XY or that. Everyone with me so far? Yeah? Does this make sense? The next thing we do is that we reduce the scope of the negation. So notice here how we have two negations, and we just simplify them. And because of that, we also had to flip the existential quantifier to the universal, the for all to an exist. But that's what happens. If we have two negations, we simply simplify them. Then we standardize the variables. So here, instead of exist y of q of xy, we can say exist of z over that. We can say that and not p of z. So that this changed. Then we can eliminate the existential quantification altogether. We can simply eliminate this to get, and we simply put what we call a function here. So instead of d, we put g of x. So basically, what happens here is that we have to drop the existential quantifier exists z q of x z, but because x was bound in this, like in a for all x here, basically with another universal quantifier, we have to make it as a function of x, some kind of function g of x, basically. This is what happened there. And this is basically something saying this function g gives us a constant that was z before, basically. And again, I'll let you, it is explained a bit in more depth here in the slide, but I'll let you read that a bit more at home. But that's the idea. And then we drop the universal quantification symbols. So we drop this for all x. This is what changed from the previous slide. So this one has been dropped. And we continue, and then we convert to conjunction of disjunctions using distributivity. So we apply distributivity from before. So initially, what happened here is that, oh God. Yes, so this P of X, we end up distributing over this term and that term also. Because we have P of X or something and something and something. So we distribute it over all those three different terms, which is what happened here. So not P of X or this, not P of X or that, not P of X or the rest. And then we create separate clauses. So now we have three and clauses, this one, and this one. We break them into three different lines in our knowledge base. And finally, we standardize the variables. So we did a few more changes here. So this X becomes changed to Z and this one to W, because we want to make sure that these are not, this X is not referring to the same, these are not equal to the ones from the previous line from before. So that's why we changed the names. And that's, yeah, and that's exactly it. And now this is basically our standard form that we had, that super complicated expression. It ends up being just these simple three sentences. And these are equivalent. Any questions on this? Yeah? When do we standardize? Why should we? Whenever you have, because this one and this one, you want it to refer to different variables, and that's why you want to make sure that you don't have this X bound to this X on two different lines. That's why you want to do that. Sorry? Yeah. Yes. So you do that here. You mean this one here? So this one got changed to X, to G of X here, this Z. Or what? No, this one. No, from here, from 3 to 4, you mean, no? Y becomes Z, yes. The reason why you do that is because you see, there's something super interesting happening here. I can explain. It's the same thing I was showing earlier in the table. This Y here is only bound by this quantifier in this part, in the middle part of the expression. This Y is a different Y, which is bound by a different quantifier. So because it's written by the same symbol, but they're actually different variables with different bounding ranges. Well, bound by different quantifiers. So as a result, it makes it more clear if we rename it. So that's why we rename it. Does this make sense? Yeah. To everyone? Okay. You can ask me also in the office hours, but that's the idea. I would say go through it at home. I know it's quite a lot, and I've gone faster on these last ones, but go through it at home step by step. It will definitely make sense. And otherwise, come to the office hours. Okay. Let's see an example, quick example. So did curiosity kill the cat? So we have Jack owns a dog. Every dog owner is an animal lover. No animal lover kills an animal. Either Jack or curiosity kill the cat, who is named Tuna. Did curiosity kill the cat? Yeah. So these are the axioms that represent what we have here. So Jack owns a dog. There exists an X which has dog of X and owns Jack of X. Every dog owner is an animal lover. There exists an X such as there exists a Y such as dog of Y and owns X. Y is owned by X, and then therefore means that X is an animal lover. No animal lover kills an animal. This is this one C. Either Jack or curiosity kill the cat, who is named Tuna, so kills Jack Tuna, or curiosity kills curiosity Tuna, and so on. Tuna is a cat. Every cat is an animal. Did the curiosity kill the cat? Any ideas? Yeah. We hear yes. Yeah. Yes. Did curiosity kill the cat, or did it? Let's see the proof. Let's do the proof through it. So these are our statements from the previous slide. So the same thing as here. So Spike is a dog, Jack owns Spike, and so on. So we wrote them in normal form. No animal lover kills a cat. This is what it says. Either Jack killed Tuna or curiosity killed Tuna. Tuna is a cat. Every cat is an animal. So the first thing we do with resolution refutation in first logic is that we add the negated goal. We add the negation. So we want to prove that we want to prove that curiosity killed the cat. So therefore, we add the negated goal. We say that that curiosity did not kill the cat, and we try to reach a refutation. Yeah, we try to disprove it, just as before. So then we say that we deduce that using, and we apply the same thing as before. So remember when we had the set of support heuristic in the propositional logic, again, we use 8 here, for example, the negated goal, and we combine with 5. So we simplify, kills Jack Tuna, kills curiosity Tuna. These are completely, so they get simplified. So we're left with kills Jack Tuna. We deduce 9. Then from 9, with 4, we deduce this one, 10. What do they have in common? So let's see, 9 and 4. 9 is kills Jack Tuna. 4 is this. So you see, this term kills is what's common, and they could be complementary literals. If we make a substitution, if we substitute for x1 with Jack and y1 with Tuna, these become complementary literals, and then we can apply the unification rule. So we can unify on kills, and we're left with the animal, these two terms, the animal lover of x1 and not one animal lover of y1. But now y1 and x1 are both instantiated to Jack and Tuna, so then we get not animal lover of Jack or not animal of Tuna. Yeah. And then we combine 10 with 3, unified over what? Or over which of these terms? Somebody. What do we unify on? So 10 with 3. So animal lover, yes, animal lover is common. And that means that we have to make x be equal to Jack. And we're left with not animal of Tuna and not dog y or not owns x or y, which is what we have here. Then we apply 11 with 1. We unify on dog of spike with dog of y. We make y equals spike. And we remain with not owns jack, spike, or not animal of tuna. We take 12 and unify with 2 on owns of jack, spike. This gets cancelled. We're left with not animal of tuna. Yeah. And now we have 13 combined with 7. So not animal of tuna with animal of x2. So we make x2 be equal to tuna. This cancel out. We're left with not cat of tuna. And then we combine 14 with 6, and we reach 40. So therefore, our negated goal was on 7, on 8. This negated goal is what introduced the contradiction. Therefore, curiosity killed the cat. Does it make sense? Any questions? Do we have time for a short quiz? Do you want to do a short exercise? Yeah? Okay, let's do it. So I know I say quiz, well, we mean like a life exercise in the class. So let's take our phones or tablets or laptops. Yeah, let's do it. The code is 278899. Is somebody still yet to join? Everyone joined? Yeah. Okay, let's get started in that case. So you still have the code here down here if you need to use. So given those clauses that we have, prove that Gabe passes CSE 140 with resolution refutation. So do it on a piece of paper. So try to bring in a paper, okay, and do exactly the same thing that we did on the slide. So don't worry about it for now about the second part, but let's do it on So let me take out. Let me put it here so you can see. So this is the proof we had before. So you have to use the same type of proof to prove that. That's here. So you start by adding the negated goal and have to apply unification rules. Have 5 minutes. Would you like me to show it also here? Let me see if I can. Um, This. So this is a question we had in the quiz 2 or 3 years ago, and the final quiz. So this could be something that could have also to do. Yeah. What's the good time? I think you need more time, right? No. Yeah. That's time was stopped. Did somebody finish it? One person. Okay. Oh, a few. 3, 4. Okay. Okay. Let's give another 1 minute. So once you do it, try to highlight in that in here. So basically highlight with colors like the order in which you eliminated them in those terms. So for with red, highlight the first one and then like and so on. I'll try to do that. And let's see what we get. Let's see the order in which you eliminated. Let's give it 30 more seconds. Okay, let's check. What did we get? So first, before we look at the answers, how do we do it? How do we? Can somebody? Yeah.
Start by acting clause saying that it doesn't pass the clause.
Exactly. So number 7 will be the negated goal. Yes. And roughly, yeah, roughly.
So then you use that with
Clause 1 on past class.
to get not pass final and from project.
Yes.
Then you use that with clause 2 to get not started the final and not final project. Then you combine that with clause 3 to get not talk to TA and gives up and not started the final or Then you combine it with clause 6 to get not talk with TA or gives up, and then you combine that with, either clause 4 or 5 to get. I did it with clause 4 to get.
You eliminate not talk with TA.
Gives up.
Yeah.
You combine with clause 5
to get false. Exactly. Yes. Yeah. Did somebody get something similar, or did somebody get a different path? Let's say a different solution. Roughly, like a different. There's multiple solutions you can get. Let's see. Yeah, I know the thing with the drawing might have been less clear, but let's see what we get. It just does okay. Okay, well, here this is something interesting. Yeah, so this is the negated goal, I'm assuming. And then you're eliminating these ones next with red. So, what? You did a different one. I see. You didn't do resolution refutation.
No, I just like this one.
Which one?
Like the disjoint one.
Which one is this joint? Which one are you talking to?
I don't know.
Oh. So in general, the idea was you start with like the colors, like the red was the first, then you go towards like yellow and green as later on as you eliminate the other ones. So the first ones are these ones eliminated, then I suppose gives up here. I don't see it. How it flows. Can somebody yeah.
The colors that are higher, which ones can cancel?
Yeah. So this one. So the goal.
The one that's circles the one that's remaining after they all cancel.
I see. This is not resolution refutation. Yes. Now I get what you mean. Yes. So 3 is cancelled out, then gives up, then fun with project, and you're left with past final or past class, and then you cancel past final here. Then study for final. Yes. Okay. Yes. I see. Yeah. This is forward chaining. Who did this? Yes. So you apply forward chaining for it, which is valid. Which is a valid way to prove it. We're hoping that the insert to use those notification, but this is all what we do is correct. It's a valid way to prove it. Yeah. Let's see this one. So what does this mean? That you first apply something on 3, and then 2. So you do 3 with 2, I suppose. So you cancel. I don't see it. What about more? What about this one? So this one says we first start with the past class. So yes, we have the negated goal, which is past class. So we cancel. We perform the rule with 1, and we eliminate past class. Then we're left with these 2. Then we eliminate study for final. You do union with 2, and we eliminate this one. On past final. Oh yeah. So if then you do past final actually. So that's the one you eliminate next. then study for final with 6, I'm assuming. 2 with 6, right? Yeah, so there's same TA with gate. This is same still forward chaining. This is doing forward chaining. You start with a TA with gate, starts with TAs, then you eliminate and so on. So this is not starting from the end from past class. It's starting from, yeah, from the givens. Yes, then there's some more. So this one is, again, this one is a representation. You start with the end with past class, then you eliminate, I suppose, this one, past final, then this one, the yellow, then the greens, and then the blue. Okay. What I was trying to say is there could be more solutions. But I was hoping, I know it didn't work out exactly as planned, but I was hoping that there's more ways you can apply rules to them. And I was hoping maybe you could see it, maybe 2 or 3 different approaches, but it's good. Okay, do we we're out of time, right? We can do I had 2 more questions, but we can do them next time, or unless we want to do them now. What do you prefer? You want to stop here? Let's stop here then, and we can continue we do the 2 more questions next time. Yeah.
Or stuff like on the quizzes, is there like a way you want us to do it, or is it like doesn't